All right. Hello, this is Nicholas Sostek.
And I'm Michael Paiva.
This is our week 4 capstone project for CEE 499.
So over this last month, we've accomplished several things. We constructed the display using 5x7 dot matrix display modules and the Max 7219 display drivers. We constructed the LED bar graph using the PCA 9955B LED driver and constructed the ADC circuit using a 16-bit ADC. We also implemented the FRAM circuit and the SD card. The SD card still does need a little bit of work. It kind of works, but not 100% yet.
All right. The project is we will be making an ammeter for an automotive application. Most of the ammeters on the market today are outdated. They have very low precision and they do not use LED screens as we are striving to use in our project.
So this is our problem statements. Most ammeters are stuck in the past, they're all analog. And it's time to update to a digital ammeter with a digital display. And we can put them in older cars to bring them in the current generation. Our objective is to design and build a digital ammeter that will monitor current drawn from the alternator and show the critical information to the operator so that they can be aware of the current status of their alternator and their electrical system in general.
Our solution is we propose to make an updated ammeter for automotive applications, as Michael has said. We plan to use an LED pixel display. We plan to have accurate measurements. We want it to be digital and not analog like they have been in the past. We would like to have non-volatile memory to store data for later use that you can look back on. And we want to be able to implement bar graphs with maximum current outputs in our design.
So the idea came because I'm building a Jeep for off-road use, and I would like to monitor the electrical system of the Jeep. In the past, I've seen other people that do this type of activity will either carry or spare alternator with them or replace it before they go out to prevent failure out in the middle of nowhere. This leads to a lot of waste and a high expense.
The importance and the expansion is this is our last project before we transition from students to engineers with our degree. We get to show everything that we have learned throughout our time in school. We get to create something different than other projects that we have been tasked with during these classes that we've taken. We could always expand it to include voltage and temperature monitoring throughout the car. We could expand it to a full alternate monitoring system that could detect would detect when the alternator fails inside of the vehicle.
So these are our marketing requirements. It needs to be easy to use, needs to measure accurately, needs to store measurement data, and needs a mechanism to retrieve the stored data.
Here's our objective tree. As you can see, the ammeters at the top. We have the store measurement data with our non-volatile memory. The mechanism to retrieve the stored data with the Bluetooth connection and or micro SD/USB port. We wanted to measure accurately with a precision shunt resistor, bad alternator detection, and high resolution ADC. We would like it to be easy to use so anybody could use it, so it can be plug and play with intuitive controls and a clear display so you can see it as you're driving, because sometimes it can get a little bumpy on the off roads.
So this is the basic theory behind an ammeter. Ammeters measure the strength of current flowing through a circuit while connected in series. The current flows through a coil and the electromagnetic field around it will generate a torque and move the needle. Basic ammeter calculation is using Ohm's law, which everyone should know by now. And the ammeters must be connected in series because you're trying to measure the sum of current flowing through the circuit. To get around putting the whole meter in series, we can use a shunt resistor, which then you measure the voltage drop across the shunt resistor, and that associates to the current flowing through the resistor.
Shunt resistors, they allow you to measure the current that exceeds the limitations of the ammeters. Shunt resistors can extend the range of any measured current while it's connected in parallel, as Michael has said. It divides the measured current and not the measured voltage, which is not what we need. And the shunt resistors can have a high power dissipation, which is very good in this application. Moving forward.
So these are our engineering requirements. The measurement accuracy will be at least 1%. That's the most important requirement, I believe. We will also need to be able to adjust the display brightness so that when driving at night or anything like that, the operator isn't blinded by very bright LEDs. And we'll have a micro SD port for storing current draw data for future data analytics.
Some of the team accomplishments, we have completed parts acquisition. We've completed the design of the overall system. We've implemented the display, the bar graph, the ADC, the FRAM memory, and the SD card writer. We wrote test codes for all of the implemented circuits that we have talked about above.
So this is the SD card controller. We can see we added an Arduino that will directly control the SD card writing, and it communicates with the Raspberry Pi Pico, which would be the main controller over I2C.
This is the bar graph display, and you can see it has all of the LEDs right here with the 5-volt going in, and you can see all the GPIO inputs and outputs that communicate with the Raspberry Pi with this chip right here.
So this is our display circuit. We will have 6 5x7 LED modules, which are these. Oh, oops. That all communicate over SPI. So SPI from the main controller will go into the first one and daisy chain to the next one. And we'll have 3 strings of 2 like this, each with their own chip select. And then you just set over SPI, you set what LEDs are on and off, and the driver will control updating the display.
Here's our ADC circuit. Here's our ADC. Here's our op amps that we have built in. And then here's our shunt resistor that will be going across the alternator so we can measure what we need to. The battery ground, the frame is right here, will be connected. And you can see how it goes out into the level shifters from the GPIO inputs and outputs.
So this is our power supply circuit. We use a switching voltage regulator here. That gives the main 5 volts out to power the Raspberry Pi Pico, to power basically everything. Then the Raspberry Pi Pico has a 3.3 volt voltage regulator on it, which then powers this OR gate. And this voltage regulator is for the vehicle accessory. So we can know when the car is turned on and when the car is turned off. So this provides like a latching mechanism so that when they turn off the car, when the car is turned off, we can sense, the Raspberry Pi Pico will sense that the car's been turned off. We'll be able to keep the power supply on long enough to write to the SD card the current draw values that are being measured. And then the Raspberry Pi Pico can then turn off safely the power supply.
Here's our level shifters. They're all the same. We use this because some of the Raspberry Pi and some of the other components need 3.3 or 5 volts. So we just need to convert it back and forth between each other to not damage anything. And you can see all the GPIO inputs and outputs right here going in and out in between each different one.
So this is the Raspberry Pi Pico. It has all the GPIOs called out here. And it's powered directly from 5 volts. And this MOSFET here will allow us to debug in circuit. So you can plug in the USB. It will take whichever voltage is higher, either the 5 volts from the power supply or the USB, without damaging anything.
All right, and here's our FRAM circuit that we'll be using for a non-volatile memory. You can see the 3.3 going in, and you can see all the GPI inputs going in, and you can see them going out from the Raspberry Pi in and out. That will gather the data and store it and write to the SD card.
So this is an image of the full circuit. Up here is the display separated out into its 6 individual digits. This is the LED driver for the bar graph. Here's the bar graph here. These are level shifters that are on a breakout board, the same way we have designed them. This is the ADC circuit, and here is the 2 op amps that we are using. And here's the Raspberry Pi Pico. And right here is the FRAM circuit.
All right, and here is the display test. As you can see, it's working properly how it should be.
And this is the bar graph test.
And Michael was able to check the reliability by leaving them on for about 4 hours and coming back, and they were both still functioning and working properly like they should.
Yep, and you can see this one is the same as the LED. It does what it's supposed to do and then dims and then brightens back up. All controlled.
So here's the power supply circuit built up with all the necessary parts. Here's the logic gates. Here is the relay latching system. And here is the buck converter that is on our breakout board that we soldered on there.
And after testing the power supply, it did not work. So at this point, we are going to simulate the circuit to make sure that we have everything correct.
Yes. The only problem with the simulation is that in multi-sim, they don't have that buck converter. So we need to create it. And that's kind of a hassle, but I think we found a way around it yesterday. So hopefully by the end of this week, we will have it fully simulated and figure out what the problem is within the circuit and get it up and running so we can move forward implementing it all together.
So this is our current Gantt chart. We have done decent. We were able to pull in some of the later stage things while working on issues with the early stage, like the ADC and the power supply. That's taking a significant amount of time. but some of the later stage, like the display and the bar graph, have all gone fairly easily.
And here's our work structure that is pretty much just what the Gantt chart is, just kind of more written out. You see all the deliverable checkpoints, the durations, all the resources, activities, the ID for them, and what needs to come before and after each one.
And this is just the work structure continued.
See, everything is there, just like the Gantt chart showed. So this is our cost estimation. This is what we have gotten for materials and the labor. As you can see, 7-segment LED display cost $1058, F-frame module $1589, Raspberry Pi 4, and so on and so on. This is what we've had to get throughout the course to make our circuit up and running. And that is our fictitious labor cost of what an average engineer makes.
Oh, this is our network diagram, and it shows the critical path from start to end.
This is our float time for our for what the network diagram shows. And you can see we have all the floats from each line and how many days it will take to complete each task at hand.
So in summary, current market ammeters work great. It's just time for an update. Using an ammeter, a user can immediately see how taxed their electrical system is. And by adding data storage, we can monitor and study the electrical system and electrical usage of a vehicle. We've designed the whole system so that it meets our needs. And we built up the entire circuit so far and tested out each part to either failure or accomplishment. And we are moving forward with complete integration and fixing any issues with the failed tests, such as the power supply and the SD card.
And this is just some of the references that we've been using when we've gone throughout this project. Amazon, Mauser, Digitech, some basic ammeter knowledge, and the Design for Electrical and Computer Engineering book. And that is our presentation for week 4, CEE 499.
Thank you.
Thank you.